Hello and welcome to the third and currently last part of my introductory series on Astron. Last time we took a look at what exists inside the infrastructure created by an Astron network. This time we will talk about what makes up that infrastructure, namely Astron and its roles. Astron is the software that runs your computers to create an Astron network, which is to say that infrastructure. For those of you who don't know yet, the D stands for daemon, which is written with AE, and putting that in the end of an executable's name is the Unix convention for naming programs that run in the background as services without direct user interaction. Astron can be built either as a standalone binary that includes all dependencies and functionalities, or as a binary and a bunch of shared objects, also called libraries. It implements roles, which are the functional parts of the infrastructure, and it is configured in a YAML file. While that file can have any name, Astron YAML is somewhat of a default name, so I will use that name in this video to refer to that configuration file. Roles, as mentioned, are a network's functional parts, and to create the whole of the infrastructure, they communicate with other roles, sometimes in the same Astron process, sometimes with ones in other processes. There are 5 or 6 kinds of roles, depending on how you want to count, and they are the MessageDirector, the ClientAgent, the StateServer or DataBaseStateServer, the database, and the EventLogger. Here's a little diagram to show you what goes where. Suffice to say for now that the database role in an Astron process connects to the actual database, Astron internal repositories connect to the MessageDirector, and Astron client repositories connect to the ClientAgent, which acts both as an Astron internal representation of the client and enforces security checks on client connections. Also, the MessageDirector, which is what routes messages, connects to and is connected to by other message directors, which is what makes this a network process. When setting up a network, you could let every process have every role, however that is not really a practical way to go about things. More likely, you will assign some roles to only a few processes. You will also have to set up how the message directors connect with each other. Now we've got an overview, so let's go into the details of each role and how it is configured, starting with the message director. Its purpose is to route messages throughout the whole of the network. To do that, the message directors interconnect to form a tree, although current plans are to make that a graph to provide better network stability. Currently, a single Astron quitting or crashing means that the network is split in two, unless it has no other message directors connecting to it. Astron internal repositories connect to a message director, which provides them with full and unchecked access to the messaging network. Message directors also keep a list of subscriptions to channels that are made by participants connected directly to them or to message directors below them in the connection tree. The algorithm for routing messages is rather straightforward. The message director routes every message upstream, and it routes it downstream to another message director if that one has registered that channel. Messages are never routed back to where they originated. Note that this also happens completely transparently to participants. Those will not have to care at all about the structure of the network or whether another participant that they want to communicate with has connected to the same or another message director. The configuration is even more simple. You just set an interface and port on which it will listen for incoming connections by other message directors, and you give it an address and port to which it should connect itself. The next role, the ClientAgent, accepts connections from Astron client repositories. When such a connection is made, the client has to provide a version string, which is set by the application using the repository, and a hash of the DC file that it uses. This is done to ensure that client and server are compatible to each other. The ClientAgent then sets a channel for the client and will run security checks to ensure that the client can take no action that exceeds the privileges assigned to it in the DC file. That includes whether the client may set interests and whether it even gets informed about interests set in its name. Connections from the client can be in one of 3 states: new, anonymous, and established. When first connecting, it is in the new state until the client sends a client hello message with the version string and DC hash as payload. The ClientAgent then puts the connection in the anonymous state and responds with a client hello resp message to inform the client of that. The client may now send messages to distributed object globals, which have been configured in the Astron YAML to accept messages from anonymous clients. Once one of them has confirmed that the client is legitimate, for instance by checking username and password against an account database, It sends a ClientAgent setState message to the ClientAgent with the payload clientState established. The ClientAgent then puts the connection in the established state. At that time, the client gets full access to the messaging network within the bounds of its privileges and visibility. Client agents have quite a lot of configuration options, and those shown here are just a small excerpt. First and foremost, they listen on a port for client connections, usually on the public interface. They also get the version string, which the client's version string must match. The astrond.yml also supplies them with a range of channels which are to be used for clients, and whether adding interests is disabled, in which case the client will have no knowledge of interests set for them, whether it is visible, in which case the client is informed of interests for it but can't set it, or whether it is enabled, in which case it may see and set interests. Another important setting is whether to use transport layer security and where to find the relevant keys and certificates. This will not only guarantee to the client that the server that it is connecting to is authentic, but it will also encrypt the connection itself. Besides being good practice in general, this will also help to foil attempts at stream hacking. Next we've got the StateServer, which is an in-memory database for distributed objects. For these, the StateServer keeps track of the values of fields as well as metadata, like on which channel an Astron Introduction repository is managing the object, or who the owner of the object is. They also take part in routing method calls and broadcast updates about field values to all interested participants that may see those updates. The only configuration option for state servers is which channel it should subscribe to for control messages. The DataBaseStateServer is practically the same, except that it also stores field values in a database if they are marked with the keyword DB in the DC file by using the database role to do so. It is configured by giving it the control channel for the database role and a range of distributed object IDs for which it will act as the state server. The database role in turn uses an actual database backend. Currently that can be MySQL, PostgreSQL, SQLite or MongoDB. Its configuration includes the role's control channel and a range of distributed object IDs to assign to newly created objects. The database and DataBaseStateServer roles do not support the creation of distributed objects with IDs that are preset by the application developer. Also, the DataBaseStateServer obviously needs the data necessary to work with the database. In the case of MySQL, PostgreSQL and MongoDB, that would be the host and port of the database backend and account information. For SQLite, it simply is the name of the file to use. Finally, there's the EventLogger, which is a bit of an odd case as it does not communicate with other roles internally. Instead, it listens to a port on which it receives loggable events as UDP packages, which it then writes into a JSON file. Currently, client agents send events to it about clients that enter, leave, or are disconnected from the network. There is also a message type, control log message, which will make the nearest MessageDirector send the message's payload to the EventLogger. Finally, Astron internal repositories also have the method writeServerEvent, which sends out such a message. In general, however, any process can send a correctly formatted message to the EventLogger, so you might want to consider IP-based access controls. Configuration is very straightforward. You specify an interface and port to listen to, a file to write to, and an interval in which to open new log files. Now that we are through with roles, there are three more things to put in your astrond.yml. First, there's the name of the daemon, which is currently unused but will eventually wind up in web frontends and the like. Second, where the event logger that this astrond should use can be found, and what DC file the network uses. Third, the IDs and classes of distributed object globals on this network, and whether anonymous clients may send messages to them. To wrap things up for today, let's talk about some best practices again. For instance, Astron internal repositories should connect to the astrond, which also hosts the state server for the distributed objects which that repository manages. This will minimize network lag and bandwidth use in the Astron network. If you have the necessary hardware, you should also run the process with the Astron internal repository on the same computer as the astrond. You should also use several client agents, as they are one of the main sources for network traffic, and distribute them in several places on the network tree. This will even out the network load. Moreover, those client agents should be on the leaves of the network tree, that is, in astronds that don't have incoming connections from other message directors. That way, if a client agent falls victim to a denial of service attack, the only part of the network affected is that astrond, instead of it and all astronds in the tree below it. Also, such a setup will only require those leaves to be visible to the outside world, and the IPs of inner nodes may be kept unknown or even unreachable. Speaking of denial of service, the current algorithm of routing all messages upstream may leave the message director at the root of the network tree swamped. On large enough networks, it would be therefore advisable not to assign any more roles to that astrond. This leads us straight into the topic of network topology. Basically, there are two extremes at or between which your network will be. On one hand, you could have one message director as the root of the network tree and have all other message directors connect to it. That way, you don't risk having your network being split in two when an astrond fails. The drawback is that you will have a higher outbound load on the root message director, as every message that reaches it and isn't processed where it originates will be routed down again. On the other hand, you could also set the network up as a balanced binary tree. That way, the chance that a message will be processed or routed downstream early will be optimized, lowering the outbound load on higher levels. Also, once messages aren't routed upstream anymore, if that's not needed, this will ease the load on the message directors higher up in the tree significantly. The drawback of this method is the possibility of a net split. Which kind of topology is right for you depends on the hardware that you have access to, the number of users, and the actual application that you are running. Basically, you will have to monitor and experiment. If you do so and find any hard facts, please drop me a line. Another important aspect is to keep track of your channels. It is helpful to organize them into sensible patterns, for instance by assigning 4-digit channels to roles, 5 digits to clients, and 6 or more digits to distributed objects. While that should be enough for any but the largest MMOs, you can easily shuffle those numbers around a bit to get larger ranges. And if 4 billion distributed objects isn't enough for you, you can always build Astron with 128-bit channels, so that you have 64 bits for object IDs. Well, and that's it with the introductory series. You now have a theoretical overview of what makes Astron tick and how to work with it. The next series will be on building and deployment, although for the moment I'm only planning to make a single video on how to build Astron on Ubuntu and add more videos as me or other people experiment with it on other operating systems and document it. The point of that is that I want to get to the actual code examples as soon as possible, so you can do more than just listen to me and instead actually make things do things. As usual, here are a lot of ways to reach me, so click, click, click now, do it, click, 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 click.